Hi guys, welcome to my channel. In this video we are going to solve a question about the steel structures, and now you can see the question is a beam as it's under the flexural loading. So now let's solve the question. But before we solve the question, if you like these videos, if you want to see more of the videos, please subscribe and share with your friends. So now let's pass the question. First I'm going to try to determine the compaction of this beam. So now how I'm going to determine it, so let's check from the specification. So I'm going to use the table of compression elements members subject to flexure. Okay, so now I'm going to use the case 10 for the flange part and case 15 for the web part. Okay, so now let's use it. I'm going to solve it here, and case 10 for flange part and B over T ratio 190 over 2 and over thickness of flange. Now we can see here 14.6. So 14.6. This is going to be 6.5. Smaller than 0.38 multiplied the modulus of elasticity over the design strength of the steel. 0.38 multiplied over 235, and this is 11.1, and so now this is smaller than the 11.1, so this is compact. The flange part is compact, right? So let's write it for the web part. It's going to be case 15, and it's going to be H over thickness of web, and this is 450, the value of D, minus 2 multiplied the thickness of flange, minus 2 multiplied 21 over 9.4. This is smaller than 3.76 modulus of elasticity over Fy. It's equal to 110. And so this is smaller than this one, so this is also compact. So now let's calculate the design load. 1.2 multiplied dead load plus 1.6 multiplied live load. And this is going to be 1.2 multiplied 4 plus 1.6 multiplied 10. And this is 20.8 kilonewton meter. And also we are going to have a moment will be created by this force. So it's going to be MD is equal to P L square over 8. So sorry, this is L. And this is going to be 20.8 multiplied 10 squared, because the length is 10 here, over 8. And this is equal to 260 kilonewton meter. Sorry, kilonewton meter is going to be a multiplication, yes, as the moment. So now we got it. Let's check for the specification what is the next step. For the next step, look at here. We are going to use, first we are going to calculate the yielding behavior, okay? We are going to calculate the yielding, and then we are going to check for the lateral torsional buckling, because look at here in the question it says that the beam is laterally restrained from the 1/3 of its length. So now we are going to check for the lateral torsional buckling. And so for the lateral torsional buckling, the length is going to be 10 over 3. Okay, so now let's solve the yielding behavior first, then we are going to do the next part. Now for yielding behavior, for yielding, it's going to be MP is equal to X, the plastic section modulus, multiplied Fy, and this is equal to 1.7 multiplied 10 power 6 and multiplied 235 multiplied 10 power minus 6. And this is going to be equal to 400 kilonewton meter as the moment. So now we got the yielding behavior. Okay, so but if you remember that I told you it's going to be so it's laterally restrained from the 1 to 3rd, so we are going to check for the lateral torsional buckling. For the lateral torsional buckling, the first we have to determine the LP and LR. Okay, so now let's check for the specification and look the formulation. So for the lateral torsional buckling, like I said before, you are going to calculate LP, LR, and also you have LB. So then due to this comparison, we are going to use one moment formula, and then we are going to obtain the moment. Okay, so now let's calculate the LR. For LP, first let's calculate for LP. It's going to be a 1.76 multiplied the radius of gyration and multiply the modulus of elasticity over Fy. And this is going to be equal to 1.76 multiplied 41.2. Look at here. I'm going to use the radius of gyration at the y direction. Okay, so now 200,000 over 235, and this is equal to 2,115 millimeter as the LP. So now let's calculate the LR, but before the calculation of LR, we are going to need a formula. And this formula is going to be RTS square. Okay, let's write it here, RTS square. I need to calculate RTS, and this is going to be the inertia at y direction multiplied the CV over the elastic section modulus at x direction, and this is going to be 16.76 multiplied 10 power 6 and multiplied 791 multiplied 10 power 9 over, we have a square root here, and this is going to be 1.5 multiplied 10 power 6, and the result is going to be 27 millimeters square. Okay, so now when I take the square root of that, RTS, it is going to be 49.26 millimeter. Okay, so now we got it. Let's write the formulation of LR. I don't need to do this part. LR is going to be calculated like this: 1.95 multiplied RTS. Okay, what is RTS? 49.26, right? And we have a modulus of elasticity multiplied the modulus of elasticity over 0.7 multiplied 235, and we have a square root here, and we have a value of J. Look at here, J in the question. I'm going to show you. J is this one. Okay, so this is going to be J 668,700 multiplied the value of C for the two part of it is flanged section. So it's C is equal to 1. This is C. Okay, so now, and this is going to be divided 1.5 multiplied 10 power 6. This is the elastic section modulus is here. Okay, elastic section modulus at x direction, and multiplied 435.4. This is H0, and now so plus, and this is 668,700 multiplied 1, the value of C, over 1.5 multiplied 10 power 6 and multiplied 435.4 square, and plus 6.76 multiplied 0.7 multiplied Fy 235 over 200,000, the modulus of elasticity, and this is also square. So from this calculation, I'm going to obtain LR as 6,804 millimeter. So now we got the LR and LP, but you know that LB is also will be 10,000 millimeter. The whole length of the beam is 10 millimeter, so it's going to be 10,000 millimeter when you convert it to millimeter, and we are going to divide it 3, and this is going to be 3,333 millimeter. Because in the question it says that the beam is laterally restrained from the 1/3 of its length. Okay, so we are going to divide the 10,000 to 3, and we are going to obtain the we are going to obtain the length of LB. Okay, the unbraced length. So now let's make a comparison, and LP is smaller than LB, and this is smaller than LR. Okay, so now we got this comparison. Due to this comparison, let's check for the specification. Due to this comparison, we are going to use this formulation to obtain the moment. But look at here, inside this formulation, we have a value of CB. Okay, and CB is going to be calculated from the moment diagram. So now let's calculate the moment. Let's draw the moment diagram and then to calculate the CB. So for the moment diagram, if you remember that for the whole length, it's going to be something like that, the moment diagram. And the formulation is going to be something like this. Look at here. And for example, this is our beam. So we have a WS force here, and the whole length is L. And we try to determine the moment at X, at the point X. Okay, so it's going to be calculated moment at X equal to equal to W multiplied 8 multiplied X over 2 minus W multiplied the L multiplied X squared, yes, over 2. Now the formulation is that if you write any point into the X, you are going to obtain that moment's value. Okay, so now let's do it. For now, it's going to be 3,333 millimeter. This is 0. Okay, this is 10,000. This is 10,000, and this is the midpoint of beam. This is 5,000, and this is 6,666. Okay, so now let's write the value of moment. If you remember that I calculated the maximum moment here. I'm gonna show you. This is the maximum moment at the section. Okay, so now let's write it. This is 260. But if I take this first part, okay, so let's write it, draw it here, first part. For example, this is like that. It's going to be a 1 quadrant. So, and it's going to be like this. So this part is, at this point, is 231. Okay, 231. And this is the first quadrant. This is the half of this length. And this is the third quadrant. So, quarter. And this is going to be 833.3 millimeter. And this is 1666.7 millimeter, and this is 3333 millimeter. Okay, this is the third quadrant. So this is going to be actually 3 multiplied 8,333. Okay, yes, I have a comma here. So now let's write this length into the X, and you're going to obtain as 79.44. And for this one, it's going to be 144.4, and for this one, it's going to be 197.5. So this is the first part of 1 2/3. But now I have to also determine for the second 1 2/3. So this is going to be, for example, like that. Okay, yeah, for example, forget about this. It's going to be something like that. This is this part, okay? From that to here. So, and this is the first quarter. It's going to be 4,14667, and the midpoint of the beam is going to be 5,000. And the next quarter is going to be 5,832, and this part is going to be 666, the last point. So now let's write these measurements, okay, these lengths into this formula, and we are going to obtain the whole moments values, okay, and this is going to be 252.8, and this is going to be 260, because you know that this is the midpoint of the beam also, and this is 252.8. Okay, so now we got it. Let's write the CB equation and obtain the value of CBs. So now this is going to be like that. This is first, 1 second, this is first, 1 to third, and this is second, 1 to third. Okay, so now let's do it for the first part. For CB, 1 second, CB for the first part, first 1 to third. So the formulation of CB was, if you remember, but let's check from the specification. The formulation of CB is this one. 12.5 multiplied the maximum moment, over 2.5 multiplied the maximum moment, plus 3 multiplied MA, plus 4 multiplied MB, and plus 3 multiplied MC. So now let's apply it. 12.5 multiplied 231, okay, for the first part. So 231, I have a comma here, and this is going to be 2.5 multiplied 231, because it is moment at max, so maximum moment, and plus 3 multiplied 79.44, and plus 4 multiplied 144.5, 3 multiplied 197.5, and this is going to be equal to 1.45. So now it's okay for the first part. Let's do it for the second part. I don't need to write the formulation because the formulation is here. Okay, CB for second 1 to third. Okay, so now let's write the formulation. It's going to be 12.5 multiplied 260. If you remember, this is 260 maximum. This is MA, this is MB, and this is MC. So let's write it. This is 2.5 multiplied 260, and plus 3 multiplied 253, and plus 4 multiplied 260, and plus 3 multiplied 253. And this is going to be equal to 1.1. And now we got both CBs, and we are going to use the smallest one, okay? Use the smallest one. So this is going to be 1.01, right? So now we got the CB, and let's calculate the moment. And for the moment, we are going to use this formulation because I told you that before. Because of this comparison, Okay, so now let's calculate it. I'm going to make this calculation here, and for the moment, let's write the formulation of the moment, and the formulation of the moment is going to be CB multiplied moment P minus MP minus 0.7 multiplied Fy and multiplied the elastic section modulus at x direction and multiplied LB minus LP over LR minus LP. And this has to be smaller than MP, right? So now let's apply it. For the application of this formula, it's going to be 1.1 multiplied 400, right? 400 minus, and 400 minus 0.7 multiplied 235, 10 power minus 6, and multiplied 1.5, 10 power 6, and multiplied 3, sorry, we have another 3 here, minus 2115 over 6804 minus 2115. So when we multiply this multiplication, we are going to obtain 363.79 kilonewton meter as the MN moment. And this is smaller than MP. If you remember, we calculated as 400 kilonewton meter as the moment. So now this is smaller than this one. So the formulation is okay, the way. So let's calculate the design. It's going to be multiplied with a coefficient. If you remember, due to LFRD, look at here, is 0.9 due to LFRD, okay? So let's calculate it here. 363.79, and this is going to be equal to 328 kilonewton meter. Now the question is solved. See you for the next question.